All right, so in this next section, we're going to spend just a few minutes talking about two important steps in our design synthesis. One is the impedance scaling, which we have covered a little bit already, and the second part is frequency mapping. Essentially, the question we're trying to answer here is, once I have my normalized filter, how do I scale it for what I really want it to do? So first of all, let's talk about frequency mappings. So there are several frequency mappings that we have to consider. The first one is the simplest one. It has to do with a question that in the normalized frequency domain, my omega c, the cutoff frequency of my normalized bandpass prototype, is equal to 1 rad per second. But I may want something else. I may want my omega c to actually be, for example, 2.4 gigahertz. So how do I basically scale things, scale my G elements? This is G4, this is G3, and so on, to have a cutoff of 1 to 2.4 or anything else that I like. What is graphed, by the way, here is the loss, the return loss of the filter, the insertion loss of the filter as a function of frequency. So the way we basically do this mapping is we do a mapping from the omega domain to the omega by omega c domain. So essentially it means everywhere you saw omega before, plug in omega by omega c. And so that means that you will have two new elements. So the L element that we had before will be the old one divided by omega c. And the C element that we need will be the old one also divided by omega c. What you will also see in this equation at the same time is the impedance scaling, which we discussed before. So I will basically multiply all my inductors with the new impedance that I want. Usually it's 50 ohms, but it doesn't have to be. And then I will divide all my capacitors with the new impedance that I want. Again, usually 50 ohms. So that's a very simple mapping. Once you do this mapping, once you replace literally all your inductors and capacitors with these new values, your transfer function will jump from a cutoff frequency of 1 to a cutoff frequency of anything else you like. There's also the inverse question. What if I want to change the filter from a band pass that I have, from a low pass that I have synthesized to a high pass? So here, basically, the mapping is we go from the omega frequency domain to a negative omega c by omega. So again, I replace exactly the same thing. Anywhere I had omega, I replace with this one. And so naturally, because of this negative, I will basically end up replacing my inductors with capacitors. So this is the old element I had. This is the new one. And clearly, I will also replace capacitors with inductors as shown here. Then there is the bandpass mapping, which is a little bit more common because most filters are bandpass or bandstop. And so again, I'm basically doing a frequency mapping from the S domain, again the omega domain, to this domain here. And this domain has two numbers that we should pay just a little bit of attention. One number is the omega naught. This is the center frequency of the filter. Usually, it's the square root, the geometric mean of the high and the low frequencies of my bandpass. And then the delta omega, which is nothing else but the difference, or as it's called, bandwidth. There's also another common bandwidth we use. We use the fractional bandwidth. So this guy here stands for fractional bandwidth. And that fractional bandwidth is nothing else but the actual bandwidth, the absolute bandwidth, divided by your omega naught, the center frequency. So once you do this mapping, basically all your inductors will end up into series resonators. That's something I have kind of given you the preview before, while all your capacitors will basically end up with shunt resonators. Now you can see a little bit, for example, why when we were doing the synthesis with the inverters, we said that you can either choose to allow your series elements to stay, right? Or you could have chosen to allow your shunt elements to stay. And this will have a big implication of what kind of resonator you need to implement. Because perhaps your physical realization of your resonator is actually an equivalent series RLC, or it may be an equivalent shunt RLC. And we will see examples of that later on. Now, the exact values of L and C are given in this graph, so I won't go any further into this. So this is a summary of all the different mappings that basically, I should say all the different mappings, all of the conventional mappings, I would say, that we have. And you can actually refer to this table to easily find out the new values that you need. So I have here a very quick example, which it's not really worth our time to go ahead and discuss here. but it basically takes you step by step into creating those mappings. So this is an example where all the G elements are known in the normalized domain, and then I want to design basically a bandpass filter. Here I'm going with a conventional approach. There are no inverters yet, and so it gives you all the new elements, and then it gives you basically, well, these are the requirements, and then it gives you essentially the a confirmation that if you were to plot the S parameters of this newly scaled prototype, you will actually get exactly what we want. Now, exactly the same scaling can happen with the topologies we have already discussed with inverters. So this is an example with a case where we have kept our series elements. So this is basically the step that we were discussing in the previous section. So up to this point, you should be comfortable with. So these are all the inverters that we have whose values are given here in the normalized domain. The next step is to basically push this, for example, to a bandpass topology. So you apply the frequency mapping that I just introduced. And if you go through the math, and you don't really have to do that, you will basically come up to this realization right here. So all my series elements ended up becoming series LC resonators. And the couplings have been scaled based on what we were discussing before to these values right here. Still, L1 prime, C1 prime can be arbitrary in this topology, and then you can simply fix the coupling sections to get the frequency response that you need. But it's quite common to have all of them resonate at exactly the same frequency because, as I said before, usually we basically make only one good resonator and not 3 or 4 or 5 of them. A very similar topology exists if you keep the shunt elements, and we will actually see this later on, the explicit topology.